Hello, welcome to the last section of Chapter 11. This is geometric probability, and it's something that I like to show students if we have a little extra time. Basically, it's finding area, and then finding the area, and then dividing. So you guys have probably heard about probability. It's the likelihood of an event occurring. You know, 50-50 equal to happen or not. 1 or 100% means it's going to happen. 0 means it's impossible. 25% unlikely, 75% more than likely. So basically, we're going to be using measurements such as lengths or area, and then we're going to find the probability of an event occurring using geometry. So let's first start with length here. Basically, if you have a line segment, the probability that if you pick a random point, say point K, that it lies on CD, so in this case, so if you pick a point, let's say I just like randomly place a point on there, the probability that it is on segment CD is the length of CD divided by the entire length of the segment, which would be AB. So here is a couple example, find the probability that a point chosen at random on PQ is on RS. So the segment that we're talking about is from P to Q. That's the entire segment. And then we want to know what is the chance that it lands on RS there. So it looks based off this picture that it should be a high likely, like somewhere between 50 and 100. Not 100, but not 50, so maybe around 75. So to calculate that, we need to know the full length of PQ, which is from 5 to -5 is 10 units, and we need to know the length of RS, which is from 4 to -2, that's 6. And so 6 out of 10 is 0.6. And so, like I said, somewhere between, around 75% just based off that picture, so that answer should make sense. And then for area, what you're going to do is you're going to calculate the area of if you choose a point at random in a region versus the entire region. So like if I pick a point and I just put it right there, okay, what's the probability that it lands in point or in the area of M? And so that's going to be what we're going to do here. So basically, like I said, you're just going to calculate area and then calculate area again and then get rid of that box there and then divide. So the diameter of the target shown at the right is 80. So this full diameter from here to there, full diameter is 80 centimeters. And the diameter of the red circle is 16 centimeters. So 16 centimeters is the red diameter. Okay, an arrow shot and hits the target. So we're going to assume that you actually hit the target somewhere. Okay, if the arrow is equally likely to land on any point on the target, what is the probability that it lands in the red circle? So what I just need to do is I need to find the area of the red circle and the area of the entire circle. So let's start with the red circle, pi r squared. So pi times the radius, the diameter is 16, so the radius is 8. So pi times 8 squared is 64. Now the entire area of the big circle, the full area, is radius is 40, so pi times 40 squared, so that's 1600. 40 squared is 1600. Know that squiggly mark there. So the pi's reduced and they're gone. That's nice. Makes my calculation a little bit easier. I'm just going to divide 64 divided by 1600 since I'm doing the percentages, and I get 0.04. So that's like 4%. So this picture does, I guess that could be 4%. Maybe not, it doesn't look like it's drawn to scale, it could be, but you have a very small chance of hitting the red circle if there's an equally likely chance. Now let's say you're a skilled bow and arrow, I don't even know what you call it, archer. If you're a skilled archer, you might be able to increase that percentage, of course. So this is just assuming that there's an equally likely chance of hitting any spot on the board. And then there's these are estimation problems. I sort of like these. They're okay. And the reason why is, I'll show you. Your dog dropped a ball in a park. A scale drawing of the park is shown. If the ball is equally likely to be anywhere in the park, estimate the probability it's in the field. Okay, so the field area is easy to calculate. All right, it's a rectangle. Okay, so it's 3 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 3 by 10. So the area of the field is 30. Now I need the area of the entire thing. And what I can do here is this part of the woods. There's 1, 2, 3, 4, 5, 6, or 7. So there's 7 by 3. So that's 21. So I have 30 plus 21. That's all of this here. I have a box there, plus 1, that's that there. And then you like have to add up all these other ones, and it's just like, this is the estimation part of it. So what I'm gonna do is I'm gonna say, okay, let's go with, this looks like 1 box, and that's 2. If I put this one and this one, that's 3. If I put this one and that one, that's 4. This one and this one is 5, and then, you know, maybe 6, and then that is 7, putting those together, so like 7 more boxes. That's why I don't, they're weird. You're not going to get an exact answer because the shape isn't a perfect thing. It's not a perfect shape, but we can find the area. So with that being said, I'm getting a full area of the 30 plus the 21 plus like 7 more approximately full boxes. So we'll say 58. So 30 divided by 58, the probability that it's in the park, we'll just put approximately here. Approximate. 51 is 0.51724, so about 51.72%. So it's about a 50-50 chance. And then the follow-up question is, well, if it's not in the field, what's the probability that's in the woods? Well, you don't have to redo the whole problem. You can just do 100% minus the 51.72%, and if you do that, it gives you 48.28% approximately again. So there you go. You'll see a problem like that on your homework. I just want to show you guys what you do in that case. I made a lot of these problems, challenge questions. I just wanted to keep the assignment a little bit shorter for you guys, and some of those starred problems are actually kind of fun. So if you're looking for something to do, give those a try. But thank you guys for tuning in to 11.7. I hope you enjoyed it.